that way. Okay? You're given those conditions, and you'll look at it and say, well, why would that happen? Okay, well, you don't need to know why it would happen, or is it happy, but it does it. Okay? You have to deal with it. My fun little animation for the day. Okay? But there's a massive but on the back end of this. Do not break your Lewis structure and curved arrow rules. This is huge behind this. Consistently, every time I've taught this so far, it comes back to these same issues that people end up breaking these rules. Okay? And I'm still not sure why it's happening. Because at no point have we ever talked about taking electrons from an oxygen. That doesn't happen. Okay? But consistently, everybody will do it through this section. Okay? And the only thing that I can kind of see that maybe is happening within this is that you've looked at what the answer is supposed to be and you say, well, I'm just going to make it do that. I'm kind of at fault for that. Okay? Because I said just make it happen. Yes, make it happen, but you have to follow rules to get there. Okay? So some of the big rules to watch out for. Do not exceed octets. Okay? Octets need to be maintained. I can't go over an octet. Do not lose octets. Okay? It's called the octet rule for a reason. Not only do we have to get to it, but then we don't lose it in the process of the reaction. Okay? There are certain cases where we will draw a structure where we're drawing a bad resonance structure and identifying reactivity within it. For instance, if we look at just the simple functional group of a carbonyl, okay, and we go through and evaluate this, we'd say, well, that structure is valid. None of my octets are exceeded. But then we can go through and look at a resonance contributor. Okay, and we have a slight issue here. Carbon doesn't have its octet. Okay? That is a slight issue. We've seen carbon without its octet. Why is it okay for carbon to not have its octet? In this case, it's resonance stabilized. Okay? That is a valid way to look at it. And what's it connected to? It's connected to a much more electronegative element. So that is a good resonance structure. The one that has started to pop up this semester and in past semesters, this isn't all of a sudden a freak occurrence this time around, is this one. What's the problem with this one? Oxygen is more electronegative than the carbon. Carbon will never take the electrons from that oxygen. And I don't have the octet on the oxygen. Okay. So if we focus on our reactions of always showing the octet be present, that should help you navigate through. So that means even under the circumstance that we just had up there, if I step back quickly enough. I'll draw it again. No, I didn't. Which totals to 8 electrons. I'll count it out again. Even under this circumstance, this shouldn't be drawn as a reactive species. The one on the right is not supposed to be involved in a mechanism. If you want to use that to explain why a mechanistic step was valid because it now has this resonance, cool. But you shouldn't be showing this as a mechanistic descriptor. Okay? It's to say, yes, this mechanism is good, not this is what I'm starting with. Because given the choice between those two structures, I always start with the one on the left because octets are satisfied. Okay? Jimmy, your question may be kind of. Can you walk through what you were saying again? I know, I'm trying to get you to say the wrong thing again and see if I can get it.
The fact that carbon's got 3 bonds, right? So it's got plus the lone pair, so to me it's a 5.
That's the word I wanted to hear. Okay, the 5. Okay. And I'm at least pushing this blame now all the way back into 130 and 151 general chemistry discussions. How many electrons are around that carbon? 8, not 5. Okay? We're not trying to count how many electrons carbon owns or anything like that. There are 8 electrons around that carbon. Every time you draw a structure, there will be how many electrons? 8. Okay? That is your signifier. I don't care how many valence electrons carbon came in with at this stage. The only time you care about valence electrons are when you're drawing the Lewis structure. It's already drawn. Okay? Valence electrons are irrelevant. Okay? And I'm not aiming that at you. It's just that number keeps popping up. Okay? Where people are counting half the number of bonds. I hate that equation. It's stupid. You should never ever see that. Okay? I'm yelling at your previous general chemistry instructors. Okay? So, do not lose the octet, do not exceed the octet. The next fun thing to do is when we're dealing with our curved arrows, move electrons from a source to a lac. Okay? I know that lac sounds kind of weird, particularly if we try and draw the reasonable Lewis structure that we just had up here for the carbonyl. If we look at our curved arrow, where did we start our curved arrow? In the bond. And I moved those electrons where? To the atom. Fair enough. Why do I only move them to that atom and not to the other atom? Well, if we look at our rules, move electrons from a source to a lac. Okay, well, if it's lacking electrons, it shouldn't have any electrons. What I just drew should be invalid. Okay? The lac is this kind of broader, weird term. Typically, you'll see it as a positive charge, but it does not have to be positive. An atom that lacks electrons can be electronegative. Very electronegative elements are grabbing electrons. Those electrons should be shown moving towards them at all times. So, some possible ways to go through and look at this. Bonds to electronegative atoms. Bonds to bonds. Okay? That one's still really kind of open in the air. Bonds to lacking electrons. So bonds to something that actually makes sense to be lacking because it's positively charged. And you can also go atoms to bonds. These are all immediate proximity. Okay? You can't jump through multiple atoms to get electrons to jump across. Okay? So be aware of that when you're trying to deal with this because we're going to see a lot of mechanisms and a lot of different atoms coming into play. We looked at water as a nucleophile. And we can reference this as a hydrate, and I'm pretty sure, oh, I did stepwise it. Our very first step can be water coming in and attacking. And then I screwed it up because I didn't show the deprotonation and protonation. So in one case, we lose the proton. In the next case, we add the proton to the other position. And we would end up at our final structure. That structure is known as a hydrate. Why is it a hydrate? We added water. Okay? And in particular, it was a nucleophilic addition because water acted as a nucleophile. So we have a nucleophilic addition. If we look at this overall reaction, we might go through and say that this is a horrible reaction to run. Okay? And some of those big things that pop up, oxygen's happy, the carbonyl's happy, are relevant. What we need to do is look at the mechanistic step. That very first mechanistic step, what do we produce? An incredibly charged structure. Not only does it have a single charge on it, it has two, and they're oppositely charged. That structure is ridiculously high in energy. Right? So what does that mean about the feasibility of producing the hydrate? Not very likely, because I can't get through that first step. So if I want to speed the reaction, I need to go through and change the dynamics of the reaction. Okay? And this can be done by adding a catalyst. The easiest catalysts are either acid catalysts or base catalysts. By adding an acid catalyst, what we do is we react with the carbonyl first. That pre-activates the carbonyl so that the water can attack easier, meaning that our electrophile becomes more electrophilic. If we run under base catalyst conditions, what we end up doing is deprotonating our water nucleophile. Well, if I remove a hydrogen from water, it becomes negative, which is now a really good nucleophile. So depending under what acid or base conditions I run, I can now change the mechanism of the reaction and maybe change the likelihood of producing the hydrate. Okay? This is something I'm fairly confident that we already talked about, or I mentioned that you guys should all go home and do, which is why I'm going to tell you now to write them up on the boards. I don't care which board you write them on, but I need a mechanism for speeding it up using a stronger nucleophile. Whoop, don't look at that. And I also need the mechanism for speeding it up using a stronger electrophile. And I don't care where you write it, front or back, but it's getting written. It's a good option. And then you had it go through an attack, our electrophile, and we end up with our charged intermediate. So really the clutch step in that case is the formation of that guy, right? Okay, which, let's make sure I don't draw on the iPad. Our clutch step is the formation of the anion. Okay, that's the big step, making that. What do you guys think? Should this reaction go faster than the neutral conditions or slower? And why? Why should it go faster? The oxygen was negatively charged in our original mechanism too. There's only one charge. In our original mechanism, under neutral conditions, I had a positive oxygen and a negative oxygen in the same structure. If we adjust the nucleophile strength, we only get one charge. It's a negative charge. Not too bad. Okay? So I might expect this reaction to go a little bit faster. If we go through and look at the electrophilic conditions, okay, you guys even added this extra step in here, which is nice, generating the H3O+. Once we've added a strong acid, that'll protonate, making a really good electrophile. Ooh, we're going to lose connectivity. Which then means our weak nucleophile in water can come in and attack, split it open. There's our clutch step again. We are probably looking at this step as again our painful step. And that said that would be this guy. Okay. Faster or slower than neutral conditions? Why is it slower? There's one charge in this case, which means it should be faster than our neutral conditions. Because under neutral conditions, we had two charges, as Will pointed out. Now we only have one charge. So we would expect this to go faster as well. What we're doing is changing that activation energy to get the reaction to go. Okay, because we're changing the intermediates being used. Kind of neat process. Okay. So if we drew this out in energy diagrams, this ends up being what we get. Okay? If we look under neutral conditions, we form that di-charged intermediate, really high in energy, not likely to happen. If we switch to either basic or acidic conditions, we end up dropping the activation energy because we're forming roughly equivalent energies as our starting material. So those steps go much, much faster under acidic and basic conditions. Chance for redeeming. What is wrong with both reactions shown up there? Nope. I appreciate the showing of how you're making the nucleophile more nucleophilic and how we're making the electrophile more electrophilic. Both of those are actually good things to show.
The arrows on the ground.
What do we say was the big deal? Everything through this chapter is equilibrium. Okay? That's why they're technically both wrong. Would you lose points on that? It really depends. Okay? This is such a strong equilibrium-based chapter that when trying to draw out a reaction, you should be showing equilibrium arrows in all of your mechanistic steps. Okay? Would I take off points? It's close. I might not. I'd avoid the risk. Okay? It may conversely turn into adding points. So if you put in equilibrium arrows, maybe you'll get extra credit points. So if you can show that you're getting those equilibrium and you're recognizing that fact, it can help. Okay? Questions about either of those reactions and going through to forming our hydrates, either in acidic conditions or under basic conditions? Good. Does it have to be water as our nucleophile? Nope. We could go through and do that with a very similarly OH labeled species. We could use an alcohol. The interesting feature in the alcohol is that I can continue to add that alcohol to form something known as an acetal. Okay. Excuse me. This is a tricky reaction to deal with. This is, again, all equilibrium based through this process. And again, you're looking at acids and bases either speeding the reaction or speeding the reaction over our neutral conditions. Okay? Which direction would we expect the equilibrium to favor? Products or reactants? It's a tricky one. Why products?
Because you're losing the pi bond.
So based on that information, it's an interesting idea. We might favor the enol over the ketone. No. I mean, there's still technically a pi bond there, so you do kind of have a quick dodge on that. Okay, when we look at directionality of reactions, we can try and predict something of pKa's, okay, pKb's, and evaluate all that fun stuff. Okay. What's the pKa of an alcohol? About 16. pKa of water? About 16. Ouch. This is a strongly equilibrium-based reaction. If I want to favor one side over the other, I have to add something to this to push it out of that equilibrium state. If I want the acetal, what can I do to my reaction? So if this is now my products, right side of the equation is my products, what can I do to the reactant side to say, hey, make me more products? I can add an excess of one of the reagents. And according to Le Chatelier, I can now push to forming more products over our reactants. What if I want the carbonyl? What if this is now switched the other direction? Okay, well, you guys already answered the question. We could add excess water. Okay. Let's go back to that reactant product one, because we missed one. What else could we do to speed the reaction or increase the amount of acetal produced? You're right, we can add excess alcohol. How about adding more of the carbonyl? It's the imbalance of our reactants which is causing the forward direction. Okay, if I have 1 and 1 of each of those, it's not going to favor one direction over the other. It's when I put in a large excess of one of those reagents that it shifts my equilibrium.
Could you remove the water?
Can we remove the water? How might we remove the water? We could try heating it up and trying to boil the water off. The issue with boiling the water off is what's going to be the boiling point of all the other intermediates? They're probably all ballpark the same, maybe a little bit lower than water, which means if anything, all it's going to do is boil off everything else except water. So not a bad idea. Not going to quite work. We can add something to dehydrate the solution. We could add a drying agent to the reaction. Right? That can help suck the water out of the reaction to help speed our reaction along. Okay? So why not the opposite? So why did I have to go back to reactant product here? Because if I had written instead that this was my product and this was my reactant, that says reactant, We could add an excess of water. What was the other option? How do we remove alcohol? It's really hard. Removing an alcohol isn't particularly easy, okay, in this case. What we might try to do is, instead of removing the water, or sorry, remove the alcohol, remove the ketone. Why might that be easier to do? We might start to get a boiling point differentiation here. So we might be able to boil the that thing out. Okay? So they are largely equilibrium driven. Deciding which way to go is going to be dependent on what you are adding to each of these. If you see water as a reagent, more than likely, what are you trying to make? The ketone, okay, our carbonyl compound. If we see alcohol present, more than likely we're trying to make the acetal. Okay? So it's a balance between those on trying to decide how this works. Okay? The mechanism that you go through and do here is identical to what you guys drew up on the board. So you did a good job. Except there's a couple extra steps that go in afterwards. Okay? Because when we go through to do this, we don't jump directly to the acetal, we jump to the hemiacetal. Okay? When we went through and did the hydrate mechanism, you only did one addition. That's your hemi step, if you will. But in the case of the hydrate, you added OH. Well, if you added a second OH, you can now make it to the full hydrate, but you already had an OH there. It looks the same. Okay? So we're really only looking at half of our mechanism when we're looking at the hydrate. As soon as we move up to the acetal, we now have that happen twice. Same steps, but it goes through and does it twice. Okay? Through all of these things, you should be identifying your nucleophiles, your electrophiles, and trying to decide where the individual pieces go. So within this one, the biggest mistakes that I've seen people make is that they look at, say, the acetal, and they say, okay, well, if I'm at the acetal and I want to make the carbonyl, what do I need to do? Well, I need a double bond to an oxygen, so I do this. Yes, you now have a double bond to an oxygen, but what happened to your R group? Okay. Now that somehow disappeared off into the ether. It doesn't just disappear. Where did our carbonyl come from? Where did that carbonyl oxygen come from or go in the course of the reaction? It turned into our water molecule. Okay? That third oxygen is a third oxygen. It's not just adding one oxygen if we compare the carbonyl to our acetal. There's technically 3 oxygens involved in this reaction. Watch out for how each of those oxygens interact with each other.
So is from the hemiacetal to the acetal, is it doing basically a backside attack from?
The exact steps in the mechanism. The exact steps in the mechanism are going to be largely dependent on acidic or basic conditions. And that is an important question. So let's go through and adjust this. We're going to tweak the nucleophile. How are we going to tweak the nucleophile? Well, instead of it being a weak nucleophile, we'll make it a strong nucleophile. How did I make it a strong nucleophile? I got rid of the hydrogen, so my alcohol acted as an acid, and it reacted with a base to now make my strong nucleophile. So I now have my strong nuke. This can go through and attack the carbonyl. You saw this already, except in the context of what you guys did. Instead of an R group, it was an H. Does the R or H do anything at this stage? Not really. It's just kind of being carried along for the ride. The result is that OR is now attached. We'd have a negative charge on the oxygen. That is now the most reactive thing present. So I need to neutralize the negative charge. What can I neutralize it with? Anything remotely acidic in solution. Why do we have to say remotely acidic? What conditions are we under? Basic conditions. So where did this acidic hydrogen come from? The alcohol that is the solvent of the reaction. That's where it's coming from. Okay? What you decide to use to pick up that hydrogen is kind of up to you, or that source. Okay? In this case, it makes the most sense to show it as an alcohol and not say, in a very sloppy mechanism, as an H+. Why? Because the H+ means we're now saying in an acid and we're under basic conditions. Okay? So it makes more sense to go through and qualify that as our alcohol as our source. The result is I now have the hemiacetal. Okay? What is our characteristic of our hemiacetal? What functional groups do we see within it? We have an alcohol in one case. I think I spelled that right. And we have an ether in the other. Okay, so if I drew, say, this compound, is that a hemiacetal? I have an ether and an alcohol. They're not, and it's not a hemiacetal because the ether and the alcohol are not connected to the exact same carbon. The hemiacetal, we have one carbon connected to two oxygens. One of those oxygens is an alcohol, one of those oxygens belongs to an ether. In the case of the structure I just drew in the blue, that's not the case. Okay, they aren't linked properly. Well, what can happen now? Because we're not at the acetal yet. What needs to happen? Okay, so a suggestion is to remove the hydrogen on the alcohol. What charge would the alcohol then become, or that oxygen become? Negative. Do I have any positive carbons floating around? No. So removing that hydrogen isn't going to help us out. What's the most reactive thing in that solution at the hemiacetal stage? The negative oxygen. Where do I want that negative oxygen to connect? The carbon that was our carbonyl. Is that carbon positive? It has two oxygens connected to it. Yeah, that's pretty positive. So ideally that would attack, and then what happens? We'd kick out the OH minus. Okay. The result would be this product. We'd have our acetal and we'd have OH minus floating around. Any objections to that? OH minus is a horrible leaving group, so that should immediately be raising red flags. However, what is it leaving into? A solution that already has a bunch of negative oxygens. So while it is a bad leaving group, relative to the environment it is leaving into, it's not that bad. Okay? No other objections? You guys are cool with that?
Is there any way to protonate that alcohol so that you have water leave and then have oxygen?
To protonate it, which is a good idea, so that we have water as a better leaving group. I do like that, but then we'd have a strong acid in a basic environment. So under the basic conditions, no. Okay? So according to this, basic conditions, I make it to the acetal. What do you mean barely? Look really subtly at our equilibrium arrows. You'll notice my equilibrium arrow is saying no. I don't make it to the acetal. And if we pop up, why is that last step not very likely? We addressed one, bad leaving group, but we said the bad leaving group isn't all that bad. Cassie, you were fishing for this answer a little bit earlier with one of your questions. What type of mechanism did I just show for this last step? Substitution, yes, is the reaction, and it is what kind of mechanistic step? SN2. For an SN2 reaction, what do I need? Good leaving group, and we negated that. We need a strong nucleophile. I have the strong nucleophile, and I'm dodging what all you guys are shouting out. Our substrate. The substrate in an SN2 reaction needs to be sterically unhindered. Primary leaving groups. Where's our leaving group? Very arguably on a tertiary carbon. Would this SN2 mechanism ever happen? Very limited control. Which means if I now try to make the acetal under a strong nucleophile condition, I do not make the acetal. It does not happen. The only thing that I really get is the hemiacetal, and the reaction stalls there. I can't go any further than the hemiacetal under basic conditions. Okay? Tricky. How do we decide that? You look at each of the mechanistic steps and decide, is that a feasible step? Every mechanism you guys have drawn out, after you've done your curved arrows, you've been like, yeah, that was a feasible step, right? You've paused every single time, asked yourself that question. I mean, if we're going to be really honest, the answer is probably no. I see you shaking your heads yes, but I don't believe you. Okay? Because in the course of this mechanism, how many times did I pause to say, is that a feasible step? Once out of 3 steps. So let's go back and check the other steps. Would that first step be reasonable? What type of mechanistic attack did I do there? Type of reaction happened in that first step? It is a nucleophilic addition. How do you know it's nucleophilic? Because that's a nucleophile. Okay, we are adding a nucleophile to the pi bond. Next step is acid-base. Okay. So in the course of making the acetal, I go through 3 mechanistic steps, a nucleophilic addition, an acid-base, and an SN2 step. And within each of those, I should be evaluating, is this equilibriumly, that's a word, favored? Okay. If not, then I have to backtrack and say, okay, I can't do that. And I try something else, and I try something else until I get all the way through. That was a bad thing to do, sorry. Any questions? Well, we just mentioned this whole new functional group of an acetal. It might be a bit silly if we could never make it. So what happens when we go under the electrophile tweak? How do I make the electrophile more electrophilic? Add an acid. The presence of a strong acid will now protonate the carbonyl oxygen, because the oxygen will act as a base, and I've done an acid-base step. The result is I now have that protonated. Is that a valid mechanistic step? Am I allowed to do that? Does oxygen want to be positive? No, so you might be screaming and throwing stuff, saying I should go back the other direction. Except what else should you evaluate? Yeah, we are under acidic conditions. What else? Is there resonance? I don't know if I actually drew it there. I didn't. We have resonance stabilization of this species, which means when I look at the mechanism, I can say, yes, this is a valid step because of the resonance stabilization. That allows for this acid-base step to occur. But you'll notice that when we try and move forward, I'm not having it attack a positive carbon, okay, a formally positive carbon. My nucleophile attacks where? The carbonyl carbon, which yes is partially positive, but it is not shown as formally positive. Why not? When I show it as formally positive, I am drawing a bad Lewis structure. Right? But if it attacks that carbon then has too many bonds. So what happens? I break the weak polar bond. And I can now make it to my product. Okay? All the same arrows end up getting used, whether you show the resonance explicitly or not. Okay? It just depends on when you show those steps. You should be drawing valid Lewis structures for each and every single one of the steps through your mechanism. We draw out our product. Is our product stable?
No.
Why not? It's charged on the oxygen. How do I stabilize that positive charge on the oxygen? It needs to get electrons. Where's the easiest source of electrons? Oh, this is the perfect slides to not be connected for. I can get the electrons from the hydrogen. I could also get the electrons from... Please connect. Our group's not particularly likely, and I've lost connection. Fantastic.